Unfortunately, because of our cultural aversion to everything fat, that has translated to an aversion to, or even a hatred of our fat cells. And the reality is, they're not there by accident, and they're not there to hurt us. There are, in fact, diseases of people who have a genetic inability to make fat cells, and they are exceptionally lean. I mean, they are ripped, as you might say. I mean, they are incredibly lean, and they're incredibly sick. They end up getting fatty tissue, fatty liver, fat storage in their muscle and bones, and they develop all kinds of diseases. So that's my weird way of introducing the fact that fat cells are essential. We need them, but wouldn't you know it, nowadays they've gone too far. And so the fat cell is a cell that is on the surface designed to store energy. So if there's an excess and the body has been signaled to store energy, and those are not the same thing. So there's energy to store, and the fat cells are being told to store it, then the fat cells will store energy for later use. But beyond the simple metabolic aspect, which we both know is the one most people are interested in, is the fact that fat cells are also a very prominent part of the endocrine system within the body. They release a myriad of hormones that do all kinds of things for metabolically beneficial, and not only beneficial to metabolism, like regulating appetite, but also regulating things as fundamental as fertility and reproduction. People don't appreciate that aspect of the fat cell. So in my mind, the fat cell's been given a bad rap. And I say that as a fat cell scientist, but at the same time, of course, it is at the center of so many of the cardiometabolic and chronic disease problems that we suffer from today that we didn't suffer from in previous generations. These so-called plagues of prosperity really can be, if you drill down, you find the fat cell at the base of so many of these issues. We call one of these depots white adipose tissue, and the other we can call brown adipose tissue. It is, in fact, because of a difference in color. One of the things we do in my lab is do fat biopsies from humans from around their belly, and we'll take out a little piece of fat from the belly, and it is very whitish, a little yellowish, and it's because it is primarily just fat. In a fat cell, it is almost entirely made up of a big drop of fat, like a bubble of fat. And it looks a little bit like Crisco almost, not quite as pristine, or like coconut oil. Maybe I'll put it that way. So that is white fat. And it's white, again, because of the incredible amount of fat. You can't see that is in those fat cells, and you can't really see anything else about the cells. In contrast, brown adipose tissue has small drops of fat within its cell, but it also has a very high preponderance of mitochondria. In mitochondria, the so-called powerhouse of the cell that everyone remembers from biology, from high school biology, the mitochondria are in fact a reddish, kind of brownish, darkly complected color. And the fat tissue that is so enriched with those mitochondria reflects that tissue. I mean, it literally reflects the light, I should say. And so it looks much more kind of reddish brown. And that not only do we see that stark difference in appearance, I mean, it actually looks more in color like muscle in color than it does other fat tissue. But with that difference in appearance is a profound difference in metabolism. And this kind of reflects the fact that white adipose tissue does indeed store fat very well. It's no surprise that white fat cells have a very low metabolic rate. Of all the cell types we've tested in my lab measuring metabolic rate in tissues, fat has by far the lowest. And then when we measure the metabolic rate of the brown adipose tissue cells, they are about 10 times higher. Its metabolic rate's about 10 times higher. In fact, it's in the same range as muscle cells. And so that's a pretty substantial effect. Now, the difference goes even one step further, that not only do the brown adipocytes have a much higher metabolic rate, but then the question is, what for? And that might sound a little academic of a question. What for? What is the metabolic rate for? By that, I simply mean, what is the cell burning that energy for? Because a cell will normally burn energy based on what the cell needs. And for example, muscle and even fat tissue basically the muscle or the fat cell will say to the mitochondria, hey, mitochondria, the cell, all of the cell, we need this much energy to do our job. So give us this much energy. And that process is very coupled. That's what we call it. It's a very tightly coupled process. An analogy for this would be like someone who's driving a stick shift car and they're revving the gas and they see the RPMs driving up, really revving up, but they're keeping their other foot on the clutch, or the car isn't in gear. And so the speedometer, the actual amount of movement in the car, is nothing. It's not matched. So the RPMs are revving, but the speed isn't moving at all. That's uncoupled. That's when we've teased the two processes apart. So the instance I was just talking about, we're revving the gas and we're moving at the same time. The car is in gear and it's going down the road. Now, as I mentioned, in the uncoupled state, which is what we have with the mitochondria in the brown tissue, that's basically when the cell isn't demanding work from the mitochondria. The mitochondria just keep burning energy. So we're revving the engine, but not because the cell needs any work done. It does, but its needs are adequately met. In this case, the mitochondria in the brown fat cells are uncoupled, as we say. And in this case, they are just burning nutrients. They're burning fat. They're burning glucose for no cellular work that the cell needs done. It's just to create heat. And heat is a chemical like waste. A biochemical waste. It is sort of the sign of a wasting of energy, back into the universe, if you will, or into the atmosphere. But in the human body, that does serve a purpose, particularly when we're babies. A newborn baby has a relatively high amount of brown fat. So amidst all the chub on the baby is a relatively high amount of brown fat. And this is good because the newborn baby doesn't have enough muscle to shiver very well. And so it stays warm. If you lift your adorable little baby out of the bathtub, and he or she is going to stay warm, not by shivering, but by having all of this brown fat that suddenly turns on and starts chewing through nutrients just to create heat. Now, as we grow and our muscles grow and our body changes substantially, the relative amount of brown fat we have drops precipitously. And then much of the fat we continue to gain throughout our life is white fat. And that's okay. It works because if we're cold, we can shiver. However, we know that adult humans who have more brown fat or whose brown fat is more active, and we can talk about that, they are much more resistant to diet-induced weight gain and diabetes and other cardiometabolic complications. Now, on the human body, the white fat is basically the fat that you can pinch and jiggle. That's all of our subcutaneous fat and a little bit of fat within the abdominal space called visceral fat. And then humans have designed little pockets of brown fat kind of sprinkled throughout the thoracic cavity and up into the neck. Now that's not a lot, but my lab has found that when the white fat cells start consuming ketones as an energy source, they will actually enhance their mitochondria number, and the mitochondria will be more uncoupled. So we found in humans that when humans were in ketosis, their fat cell metabolic rate went up by 3 times. Now, that didn't get up to the 10 times higher that you see with brown fat, but still a tripling of the metabolic rate of fat cells is nothing to sneeze at. So it's like the white fat cell hasn't fully become a brown fat cell. It hasn't, and it can't, but it started to act a little bit like those brown fat cells. So it's not quite brown, but it's not quite white anymore. It's beige. And so we say that it was a beiging effect. So we found that the ketones have a beiging effect on the white fat, increasing their mitochondrial content and making the mitochondria behave in a more uncoupled state. Now, it's no surprise to people to learn that cold immersion will do the same thing, but that's, of course, a much less pleasant phenomenon by many standards than just being in ketosis through fasting or dietary control. But nevertheless, it does touch on the fact that you can leverage this biochemical phenomenon to have your fat cells start to really work in your favor in order to facilitate weight loss. So ironically, the fat cell begins eating its own fat as its metabolic rate has climbed, further facilitating fat loss. I know of no evidence to suggest that it can ever go all the way. I don't believe that could be possible. It would take a remarkable series of events and very likely nothing that the body could do on its own. Maybe someday some drug interventions or some injectable treatments. As the kind of cell biologist, fat scientist, there's a part of me that would think, oh yeah, that would be great to control obesity, but it would be catastrophic to things like appetite control and fertility, because brown fat cells do not behave in the same endocrine fashion as white fat cells. Like, for example, we've touched on a little bit fertility. Leptin, while we always think of leptin as only regulating appetite, it is utterly and totally essential to fertility. That's why if someone has a leptin deficiency, they are infertile. They're sterile. They cannot reproduce. You have to give them leptin in order for them to have a normal fertility capability. But brown fat cells produce essentially no leptin. And so it would be, in a way, catastrophic to the species, if we had people who were suddenly shifting over. Not only catastrophic to the species, no reproduction, but even to their own health. Especially a woman whose body thrives on the remarkably dynamic cycling of the hormones that swing around so remarkably during a menstrual and ovulatory cycle. That would basically all be stopped in the absence of leptin. And that would be very bad for bone health, very bad for mental, emotional health. Now, I know I'm not a woman. I sometimes get a lot of heat that people suppose I can't talk about it. I'm an endocrine expert. I teach graduate level endocrinology courses, and I'm a fat cell scientist. So there are some things I can speak to as an authority, not because I'm a woman, but because I know hormones. Yeah, as much as it would sound like it's a good thing, let's kind of go all the way. Not that either of us is suggesting it. There would absolutely be consequences, and they wouldn't be good. I think that the sweet spot is through fasting and optimized lifestyle habits, you can sort of push the fat cell a little bit that direction, and you just get a little bit of that advantage, the metabolic advantage, without losing the fundamental necessity of the white fat in the first place. Brown adipose tissue is completely mingled through the ribs and then up into the clavicular space and up into the neck just a bit. It's an odd location, right? And it's certainly not something you can look at and say, well, gosh, my brown fat sure is getting big. You wouldn't see it because it's so enmeshed within the cavity itself. My speculation is that we have brown fat there in order to ensure all of the blood that's going to be coming up into the brain is warm in the event that the body is very cold. That if we're cold everywhere else, like you're immersed in an ice bath, you can shiver because you have muscles everywhere from your neck down. Well, we have no muscles up in our head. There's no muscles to shiver to keep the brain warm. And so we have these little incubators around all of these blood vessels coming up, particularly the carotid vessels. And we can warm all of the blood up before it gets to the brain. That is admittedly a little speculation, but I'm confident in it. Sex hormones largely determine where a person stores their fat. And when you look at a little boy and a little girl who are growing up, they look identical in their body shape. There's no difference until they reach puberty. And then the moment the sex hormones come into play, the sex hormones, among the many effects they're having, metabolically speaking, determine where the body will store fat. They're literally, like estradiol is literally enhancing the expression of enzymes that will dictate fat storage at breasts, hips, and buttocks, the kind of prototypical female sites. Whereas the androgens are largely inert. They don't really promote fat storage anywhere, but the only hint of it is centrally, abdominal. Now, all of that is white adipose tissue. Anything you can pin, and that is particularly true in females, because females relatively store so much more of their fat as subcutaneous fat than males do. Part of the androgen effect of fat storage is a little more visceral fat. So that's the fat that is enmeshed around the organs behind the muscle of the stomach. But but the estrogen's effect on fat storage is overwhelmingly subcutaneous. And that's good because, one, subcutaneous fat produces more leptin than visceral fat does. And two, if you have a woman who's storing a lot of fat viscerally, especially during her reproductive years, it may complicate the fact that you're about to grow a baby there. And now that the fetus is in the growing uterus is competing for very limited space with all of that visceral fat tissue. The visceral fat would be like actually pressing in on that very area. And so it's no surprise to me that the female phenotype is designed more to store fat subcutaneously because it gets the fat out of the way of that critical area on her body for fertility. Women do naturally have a higher set point for adipose tissue. It is supposed to be that way. Part of it is the necessity for leptin. Women's female fertility is much more dependent on a higher amount of leptin than male fertility is. And I believe, here's a little more speculation, but it's informed, that that reflects the fact that the female body bears the metabolic burden of fertility. The male has a brief, wonderful moment, and then his role in essential role in fertility is over. Now, I would submit that the dad has a profound role through the life of the child, of course. But even still, the burden, if you will, and I don't want to use that term may be too loaded because having had a wife who was pregnant multiple times and we have beautiful children, it's also incredible, but it is a burden on her body, a metabolic burden.
It's physically and chemically demanding.
Yeah.
Absolutely.
Yeah. Good.
Yeah.
Right. Yeah, you said it. That's right. So her body carries that metabolic burden. And basically, my thought is that her brain needs to know that there's enough fat on her body to carry that baby, to develop that baby, to gestate that baby, because her metabolic rate will be higher during pregnancy than it has been at any other point in her entire life, because she is working so hard to grow her own tissue and to give the energy to the baby to grow the baby. And then even when baby's born during lactation, her metabolic rate stays very, very high because she's still producing enough energy for two. It's basically the brain's way of saying, hey, fat cells, is there enough of you that if we suddenly had reduced access to food, you have a lot of fat on you and we can carry this baby? Now, that I don't mean to assume like starvation. That would, of course, be a big problem. But it's basically the brain's way of ensuring there's enough stored fat that it is okay allowing fertility to move forward. and that is through leptin. If there's enough fat cells, there's enough leptin going to the brain, and the brain will turn on this gonadotropin pathway, going to the pituitary, then going down to the ovaries and telling everything that it can go forward. If there's not enough fat cells, there's not enough leptin, then the brain will shut that pathway off. It will turn off that axis of that gonadotropin releasing hormone from the hypothalamus, and then everything downstream of it. The pituitary will turn off its follicle stimulating hormone and luteinizing hormone, and the ovaries will just reduce all of those sex hormones. And then fertility would stop, ovulation would stop. That reflects the fact that her body bears the metabolic burden, not only of the gestation, but also of the lactation and feeding the baby. And so it's no surprise that it's a very, very complicated affair. But all of it, even still, comes back down to the humble and often misaligned fat cells. Insulin resistance has two aspects of itself. One is the pathological side, which is the version of insulin resistance which promotes chronic disease, these so-called plagues of prosperity, Alzheimer's disease, fatty liver disease, hypertension, heart disease. All of those are consequences of insulin resistance and the pathological version of it. But there is a physiological side of insulin resistance, which is when the body becomes acutely insulin resistant to serve a specific purpose. And that is the insulin resistance that we're touching on now when we talk about the changes, particularly during the menstrual cycle. So a woman will become relatively a little more insulin resistant. It's right as the endometrium is kind of at its thickest and progesterone is peaking. Then she is at her peak insulin resistance during that cycle. Now, it does not get to the point of like clinically problematic. But if her insulin resistance were humming along throughout the month at a very, very low level, or let me say it another way, she's very insulin sensitive throughout the entire cycle. And then with those few days, right around the time of ovulation and progesterone has come up, then she becomes a little insulin resistant. And then as she starts to shed, there's no implantation, no fertilization, then things go right back to insulin sensitive. The estrogens tell the body where to store fat, but not how much fat. That's very, very important. Overall, estrogen actually has a fat burning effect. This is why at any moment in time, a woman is burning relatively 40% more fat than a man is. Now, a man has a higher metabolic rate just because he's bigger, but a woman, relative to her body weight, will be burning 40% more of her energy from fat. And that is very, very heavily dependent on the estrogens. So estrogens tell her where to store fat, but also tell the body to rely on that fat. So a lot of fat is going into those fat cells, but a lot of it's coming out to be burned. So there's a high turnover. That's a very healthy way to store fat. Progesterone tells the body to store fat, and it does so by leveraging insulin. And so during that period of time, progesterone promotes a slightly insulin resistant body, and that means insulin levels have to come up a little higher to overcome this subtle insulin resistance, throughout the entire body. But that doesn't happen at the fat cells. The fat cells do not become insulin resistant. And so now this higher than normal insulin promotes a slightly greater than normal fat storage. So hormones like progesterone and insulin tell the body how much fat to store, whereas the sex hormones, progesterone's a sex hormone, so the estrogens and androgens tell the body where to store fat. And those are not the same thing, of course. So there is that acute little moment of insulin resistance, nothing to be concerned with. After her fertile years have passed her by, and as you noted, at that point, the aromatase expression changes in the ovaries, and her estrogens production starts to drop a lot. At that point, she's lost that kind of fat-friendly and even protective effect of the estrogens, and now she's sort of subject to the whims of the androgens a little more with regards to fat storage. Now, this is not to say her androgen levels go up really high. No. They don't change that much. It's just that the estrogens
it's a relative amount.
That's right.
Relative amount, yeah.
Perfect. That's perfectly right. And so now her body just starts to store fat in more of an androgenic way. In other words, as you perfectly mentioned a moment ago, more centrally. And she can literally start to lose some of that fat that she had been storing on her breasts, hips, and buttocks, because the estrogens were what was determining where that fat should be stored. And that then starts to, in a way, that at that point, the woman starts to lose the metabolic protection that the estrogens had provided her. Estrogens, in a way, provide a metabolic protection for a woman, allowing her to basically avoid the consequences of her fat tissue, the metabolic negative consequences. She's been protected from it. Estrogens help her body know what to do with fat and handle the fat in a good way. With the loss of those estrogens during menopause, now she's no more protected from the fat than her male counterpart is. Her risk of disease from fat tissue starts to match that in the males. If you were to take a fat biopsy from a woman and a fat biopsy from a man, and if you were able to put those fat biopsy tissue, the fat tissue, in a little beaker in a science lab and keep the tissue alive and active, it would literally be secreting 40% more of its fat at any moment than the fat cells from the male, from that same location. You pop it out of the belly. So you invoking the muscle, that could be part of the demand. In other words, the pull, where there could be a differential expression from the female muscle cells. I don't know this, so I'm speculating, but muscle tissue releases a myriad of hormones as well. And it could be that that there's a difference in expression of hormones, hormones like FGF21, for example. That is a muscle-derived hormone that can activate lipolysis. I don't know about that. I can't speak to it, but I do know that the estrogen effects simply enhance lipolysis on their own. So we can remove the muscle from the equation, although in the whole body we can't, and I believe it's very likely relevant. But just sticking with the sex hormones and the fat cell, Estrogens simply activate lipolysis at a higher rate, especially at subcutaneous fat cells. And the differences go even further. The estrogens not only tell the body where to store fat, but also how to store it. One of the reasons females can store more fat than males pre-menopause and be much, much healthier is that the very nature of her fat cells is different because of the estrogens. Estrogens, specifically, particularly at the buttocks and hips, much to the woman's dismay perhaps, provide an almost limitless phenomenon of hyperplasia. So anytime the insulin or the progesterone is telling her body to store more fat, because they control how much fat the body stores, the estrogens will tell those tissues, buttocks, the fat tissue in the buttocks and hips, hey, the moment the fat cell gets a little big, just recruit another fat cell and recruit another fat cell and another fat cell. So she continues to store her fat there by making new fat cells. That might sound like a problem, and it might be a problem if she's trying to squeeze into her college jeans that she used to wear. But metabolically speaking, it's magic, because when fat tissue is growing through hyperplasia, the fat cells stay small and they stay very metabolically healthy. In men who have relatively much lower levels of estrogens, there is none of this hyperplastic stimulus. And so his fat cells, if there is a pressure to grow, not through progesterone, of course, exclusively through insulin, they almost totally grow through a process of hypertrophy. And the fatter the fat cell gets, the sicker it gets and begins to promote insulin resistance throughout the body. So the protective effects of the estrogens go through multiple levels here, not only burning fat at a higher rate at any moment, but also altering the very nature of how she stores fat at those locations particularly. As she is storing more fat, her fat cell number starts to go down. But again, that's not a great thing, because that does mean, in the absence of any other changes, and Stephanie, you mentioned it very, very well, to me, there's an opportunity there for lifestyle change. But as she starts to lose her fat cell number, if she continues to eat the same way and live the same life, then her body still wants to store that fat. It just has to store the fat now in fewer fat cells, inducing a greater and greater hypertrophy, and perhaps storing the fat in tissues not designed for long-term fat storage, like the liver and the muscle, etc. So she loses multiple protective benefits. Again, that all plays into why I say estrogen allows the woman to be a metabolic superhero. And with the loss of that estrogen, she just becomes a mere mortal. When the fat cell gets too big, we almost have to feel bad for it, because it starts to try to survive. But the two ways that I'll mention in a moment in which that it leverages in order to survive end up, unfortunately, creating metabolic havoc for the rest of the body. When the fat cells are hypertrophying too much, they begin to actually push each other further and further away from capillaries, blood vessels. And the capillary is the site of exchange for a cell. It's where it gets new oxygen. It's where it dumps off its CO2 from its metabolism. It's where it receives new nutrients or gives out its nutrients. And so suffice it to say, a cell has to be very, very close to a capillary in order for that to work. But as the cells are hypertrophying so much, now it used to have maybe a micron or two away from a capillary. Now it's getting several. It's increasing multiples in distance. That is catastrophic. It will literally die. It will suffocate. And it will undergo a process called necrosis. It will rot and die. And we don't want that. So the hypertrophic fat cell, who senses that it's becoming increasingly hypoxic or reduced in oxygen access, it will start to secrete pro-inflammatory cytokines, because some of those cytokines will induce the production of new blood vessels. So this is the big fat cell's way of saying, hey, capillary, you're too far now. I'm sending you this message. Bud off, branch off a little capillary to come out this way so that I can start to get some blood so that I don't die. Now, that helps the hypertrophic fat cell survive, but at the same time, it's secreted a whole panel of pro-inflammatory proteins, only some of which, largely one, is actually helping with the improved blood flow. But it just sort of belches them all out. And then it's all the rest of these pro-inflammatory cytokines that begin to promote a subtle but relevant inflammation throughout the entire body. Like the body is fighting a mild infection in the absence of any actual infectious agent. It's just this fat cell doesn't know what else to do. At the same time, the fat cell is reaching a point of maximum dimension. And I know of no comparable effect where you can take a normal-sized fat cell and in the presence of insulin to promote its growth, it can grow to 10 times its volume. And unlike any other phenomenon in the body, where it will grow 10 times. And at that point, it begins to reach a point of maximum dimension, where it simply starts to tell itself, I can't grow anymore, or I will overwhelm the ability of the cell membrane to hold us all together, and we will literally burst apart. And so the hypertrophic fat cell starts to tell insulin, you want me to keep growing. And so while I can't stop you from shoving the nutrients in, because it can't really, I can stop you from preventing me from breaking down my fat and leaking out my fatty acids. So that's what happens. I know I got that a little complicated with a bunch of double negatives, but basically insulin would tell the fat cell, don't break down any fat. In other words, inhibit lipolysis. Lipolysis is the technical term for breaking down stored fat. But the hypertrophic fat cell says to insulin, I can't stay this big. I can't continue to grow like you want me to. So fat keeps coming in, but now the hypertrophic fat cell starts letting fat out. And so we have two phenomena occurring in the body overall because of the hypertrophic fat cell. One, the body's becoming ever more inflamed. And two, the body's becoming filled with circulating fat that it doesn't know what to do with. Those free fatty acids that it can't burn because insulin's too high. And if insulin's high, the body doesn't burn fat. It can't really store in the fat cells anymore because the fat cells are already too full. And so then you have this more ectopic fat deposition that we've both alluded to already, where you start storing fat in tissues that are poorly designed for fat storage, creating things like fatty liver disease, and that could progress into full-on steatohepatitis and cirrhosis and liver failure and myriad other problems. But it all comes back to this series of events, a fat cell that has become overfull, or in other words, hypertrophic. And then to bring that back to the female phenotype, it starts to happen with the loss of estrogens. You can't do that. And I would submit you wouldn't want to. So what you would want to do, rather than just correcting the fat cell's ability to respond to insulin, what you'd want to do is allow it to respond well to insulin. And while you cannot control the effect of the fat cell, you can control the insulin. So don't look at correcting the fat cell. You can't. It's out of your hands. You can correct the insulin. And that comes back to all the strategies we've talked about before, and I know you've talked about in other podcasts. So we can't blame the fat cell for just doing its job, and so we shouldn't try to correct it. What we should try to correct is the stimulus that continues to aggravate the fat cell, because that we can correct. Glucagon is insulin's opposite, the yang to the yin, and that is reflected in multiple cellular processes. The most obvious is their battling effect with glucose, whereas insulin wants to lower glucose at any moment of time. Glucagon wants to increase it. But the differences continue. And it's in a way thematically represented by the fact that insulin wants to store energy in the body. Glucagon wants to burn it. Ketogenesis is the process of burning a lot of fat and turning it into ketones. Well, it's no surprise that insulin inhibits that, because insulin doesn't like burning things. It just wants to store them. And it's no surprise to learn that glucagon activates that. It stimulates it. So it's the balance of these two hormones that, in a way, have a profound whole body effect on nutrient metabolism. And now you mentioned protein. It's interesting to note what protein does. I'm an enormous advocate of dietary protein. I think most people don't get enough of it, and they're accidentally avoiding the best sources of it, or deliberately avoiding the best sources of protein. But protein will have a variable effect on insulin and glucagon. If someone has very, very high glucose levels, then protein can have, in fact, an not inconsequential effect on increasing insulin. So if you have protein in the midst of high glucose, it can be pretty significantly insulinogenic. And then this overall ratio of insulin to glucagon gets quite skewed. However, if the protein is being consumed with fat, as it is in nature, there is literally no exception to this. In nature, all protein comes with fat. Always. In our hubris and our fear of fat, we've pulled the two apart, thinking we know better than nature does. So I'll just talk about protein alone. But if the protein is coming into the body in the absence of a high glucose level in the blood, then the insulin effect is essentially non-existent. It may be there, but it's very, very modest. And this has actually played out in multiple human studies. I very much resent people saying that protein has a significant insulin effect, because I can disprove that so readily through so many human studies. It doesn't in the absence of glucose or in a normal glucose level, but it does increase glucagon. And so overall, the net metabolic effect of the protein is metabolically favorable in that it is going to help the body use energy rather than just store it. Not to mention the fact that protein has a very good effect on satiety, and protein increases metabolic rate because of the act of digesting and absorbing it more than the other nutrients do. So for all of those reasons and more, I'm an advocate of protein, but that even is reflected in these hormones like insulin and glucagon, and others like ghrelin that would stimulate hunger that goes down, and other hormones like GLP-1. But suffice it to say, I'm an advocate of protein. I know you are too. And the overall, the net effect on the metabolic state of the body is reflected in a way with the changes in insulin to glucagon in their ratio. To my knowledge, the only instance where protein comes with glucose or a carbohydrate source is dairy. And in fact, dairy, as mommy mammal is producing this perfect food for baby mammal, it is high in all three macronutrients. It's high in fats and proteins and lactose, or what becomes glucose. And I look at that and think, what a perfect formula to stimulate as rapid growth as possible. And so if there is an insulin effect from that protein and that lactose, which there would be, there certainly is, then all the better, because it's going to help that baby grow. And it will help that baby have adequate fat tissue, which that baby desperately needs in order to make ketones for its brain growth. Not to go on a tangent like that, but a newborn baby will get into deeper ketosis after 2 or 3 hours of not eating than an adult will in 2 or 3 days. A baby is in a massively fat-burning ketotic state. And the thought of the reason for that is very likely because ketones are such a profoundly beneficial fuel for the brain. And this is why a baby that is born underweight may develop learning disabilities later because of, in fact, a little stunted brain growth. You need those fats and those ketones to adequately fuel the brain. There's a whole area of research on this, which I can only lightly speak to, but I'd encourage anyone to look up a book by the work by a scientist who's up in Quebec, actually, named Stephen Cunnane. And his book is called Survival of the Fattest, which I love. But it is brilliant work. And he sort of posits an alternative theory of human evolution. Of course, it's all a theory. All of evolution is a theory, after all. But it's very, very compelling. And it really puts fat tissue in a primary position. And of course, he backs it up with very significant data. But I believe that's the only source of protein in nature that comes with a high carbohydrate load as well. And I don't think it's an accident that it happens to be the one food that is specifically designed to help a human or any animal grow as quickly as possible. Yeah, so my professional opinion will only rely on peer-reviewed studies in humans. The best source of protein is any animal source protein. Now, I know this starts to touch on very culturally sensitive ideas, and I'm certainly sensitive to those. I truly am. I hope I never am too flippant or irreverent talking about people's kind of ethics and morals. Even if I disagree with them even profoundly, I still want to be respectful. But the fact is, every animal source protein has a higher digestibility and absorption and better amino acid profile than any plant-sourced protein. That's just reality. And I can just speak to that. And that's also, I think, reflected in nature. Throughout all of human existence, we would have gotten our proteins from animal sources. Thank goodness. And indeed, Stephen Cunnane's work touches on this. And so do other evolutionary biologists from Harvard who posited many, many years ago a theory called the expensive tissue hypothesis of human evolution, which basically stated that humans deviated from other primates because they started eating high-fat animal foods. And that is unlike other primates. Most other primates primarily subsist on plant matter. And that allowed the human body to change in two very, very meaningful ways. By eating very high nutrient dense foods, which all animal foods are, by orders of magnitude more nutrient dense than any plant foods, it allowed the intestines to get significantly shorter. And indeed, our intestines are significantly shorter, especially our large intestine, compared to any other primate, because we didn't have to ferment stuff. It just, everything we ate was so immediately digestible and absorbable that we could shrink everything, especially the large intestine. We didn't need it anymore, basically. And at the same time, because we were eating such nutrient-dense foods, we allowed our brain to get significantly bigger. So again, that's what's called the expensive tissue hypothesis. This is just undeniable. Humans are built, we are designed to eat animal-sourced foods. Now, again, people may have their own reasons for avoiding them, and I can't speak to that, but it cannot be due to a hope to be healthier and stronger, because the further a human gets from animal-sourced foods, the more nutrient deficient they will start to become. And so they need to, so something like veganism requires not only a high level of education to be aware of the nutrients that you will be deficient in, because you will be. That's just a reality. I don't mean to speak evil of that paradigm of eating, but you will be deficient in nutrients, so you have to know what those are, and you have to just make sure you can afford the good supplements, the high-quality supplements, to make up for those deficiencies.
More women, at least in my observation, I could be wrong here, but more women tend to be attracted to and try the vegan diet. So what often happens, and I would actually say this is true for the ketogenic diet for women as well, but like you start this new intervention, right? So maybe it's vegetarianism or veganism. And they feel initially a lot better, right? Like they start eating more plants and they have more energy and their skin clears up and all the things. And it's probably a proxy of eating more plants than they were prior. But then, you sort of ride that sort of maximal benefit, like that area under the curve, and you sort of get to the other side of the curve, and then the hair starts falling out and, their energy tanks, and, some of the initial complaints around why they maybe from a dietary perspective, like forget the ethics and the environmental argument for a moment, they start to experience maybe some deleterious effects from the diet. And then what ends up happening, at least in my observation, is a lot of women will say, gosh, like I just got to do this diet harder. Like I just got to be as strict as I was when I first started, right? Rather than maybe saying, okay, maybe I've actually ridden the maximal benefit curve of this diet now. That metabolic intervention of having more plants has kind of served its purpose. Maybe I need to reintroduce some animal proteins and become the omnivore, and kind of in line with that, that teleologic or that evolutionary lens that you just provided. And what I so often see in terms of nutrient deficiencies, it's like the B vitamins are not there. We have, and they're not able to, to be a vegan. I think you need to be very, you almost have to be a chemist, because you have to know what foods to combine, because you're not getting the full complement of like amino acids, let's say, because plant-based protein sources are incomplete by nature. And as you said, they're not as bioavailable. And in order to kind of trigger, we've been talking about protein, and I like to talk about protein in the context of body composition, in terms of maintaining muscle mass and bone mass, there needs to be sort of like a minimum amount of leucine, one of the amino acids that we consume, in order to drive muscle protein synthesis. And you don't really get that in the equivalent. Like if you take a scoop of, I know we're just talking only protein right now, which, to your point, doesn't occur other than a whey protein powder, right? But if you take like a scoop of whey protein, right, versus like pea protein, like scoop for scoop, you're going to have to consume, I remember doing the math on this for my book, it was like around 25 to 40% more of the plant protein compared to the animal-based protein. So then for those women that are like, okay, I'm trying to lose weight, now you're consuming 25 to 40% more calories, right? So now this also this also gets thrown into the metabolic mix where you are constantly needing to overconsume calories in order to get that minimum viable kind of protein, that MVP, maybe, if you will, in order to kind of drive that MPS, that muscle protein synthesis.
And I would add, before we move on, the problem with many of these plant proteins as well is that as you concentrate the peas, for example, to get the protein from them, it's those amino acids that you want to get. But as you concentrate those peas to such a high level, because peas are so deficient in amino acids generally, you need a lot of pea to get to just that serving of amino acid. What you inadvertently can concentrate as well are the metals, the natural levels of lead and arsenic that are just in plants. So this is a known phenomenon. People have quantified the amount of heavy metals you get in protein supplements, and the plant proteins are always the biggest offenders. I think it's interesting, once again, to note as we look back in time, not back enough to explore the theories of evolution, but just in previous generations, particularly in Asian cultures, it's fascinating to me to look at these cultures that have relied on plant proteins to various degrees, although I'm unaware of any that relied exclusively on them. Like, for example, those who would make tofu. It's interesting to me to note that around the world, South America or Asia, when they were relying more heavily on plants, they would always engage a process of fermentation. Fermentation is so powerful because it makes foodstuff much more absorbable. By fermenting the soy, for example, you have eliminated not only metals, but also anti-nutrients like the phytates and the oxalates. They get cut back. They get eliminated basically through the fermentation. And so now all of a sudden, when you're eating that fermented plant matter, now you can in fact digest much, much more of it than you would have otherwise. So to me, there's an opportunity that if someone wants to, or in their mind has to get their protein from plant sources, then my encouragement would simply to be eat it the way humans used to eat it, and in some places still do. Get it from fermented sources. If it's not fermented, you're wasting a lot of money and you're getting a lot of stuff that you don't want. I have very strong feelings about it because I believe that whether it's deliberate or accidental, data has been horrifically misunderstood or even construed to fit an ideology. So a few things. In humans, we have zero evidence that proves that protein consumption will reduce longevity. There's no conclusive evidence. We have correlational evidence that is all over the board. Even Walter Longo's own work found that there was during their 50s, people who ate the most protein tended to have the highest mortality, which would fit that overall view that protein promotes mortality. But even in his own published data, at around the age of 60, 65, it went inverse. It flipped. And at that point, the people who ate the most protein had the lowest mortality. And that is a theme that has been published across multiple papers, particularly in the recent probably 10-ish years. So suffice it to say, the evidence on humans with protein and longevity is very, very complicated. And there's no evidence to suggest conclusively one way or the other. I would say that part of what's important, as you noted, is that the older we get, the more protein we need to sustain our lean mass. And muscle and bone mass is one of the greatest predictors of mortality. Inversely, people with the highest muscle mass are the least likely to die. Well, good luck maintaining muscle mass if you're not eating a lot of protein. Now, if we leave the humans to the side for a moment and we get more mechanistically into animal models where we can control everything, we can measure them their entire life from the day they're born to the day they die. Animal models like mice who have a slight protein deficiency in their diet will live a little longer than the animals that have ad libitum or free access to protein. That supports that general idea. However, they also have almost no fertility. They do not reproduce. And that is sort of this irony that, yeah, sure, you can live longer, but what good is your life if you can't, there's no family involved in this. Now, again, we have to be cautious trying to translate the animal studies to the human studies. And these animals are living in a perfectly controlled little box, literally their whole life. And so their muscle mass doesn't matter as much. They're not a human who's walking through the kitchen who stumbles and now has to grab the counter to stop themselves from falling. And if they don't have enough muscle mass, well, they didn't stop themselves. They hit their head, they broke their hip, and now they're going to die. Now, however, in the midst of this kind of poo-pooing dietary protein and wanting to avoid it for living longer, we not only have to appreciate the effect of the muscle, but we have to kind of desperately appreciate the fact that with humans and our survival, depending on the maintenance of our lean mass and the maintenance of our brain and the fats that come with those brains, the further we're getting from animal sourced foods, the more nutrient deficient we're becoming, not only in nutrients at a kind of micro level, but also just good fats and these best proteins. We don't want to avoid protein in an effort to live longer. Moreover, I guess back to the fertility aspect, in men at least, we know that the further men get from animal sourced foods, the lower their testosterone levels are and the lower their sperm quality gets. So this to me further suggests the fact that a diet that is devoid of animal products is a diet that is incompatible to the human species. And
kind of coming back to, we were talking about, a menopausal woman, let's say now she doesn't have that estrogen protective effect and her fats become a bit more hypertrophic. If we are able to maintain or even add to her lean muscle mass, let's say, then that like one of the things we know about muscle, of course, is it is a beautiful glucose sink, right? It's a kind of independent of insulin, really. It can kind of take glucose up, phosphorylate it, and then it kind of stays in the muscle for the use of the musculoskeletal system. And then now when we have a, musculoskeletal system, we'll say, that can take in excess glucose, then you're negating the need, we'll say, for insulin to kind of pump, like get ready and rev up and get the glucose out of the bloodstream. And we're going to be protecting that fat cell from becoming too big, right? So then we're protecting that hypertrophic effect as well.
And I am an enormous advocate of resistance training. In fact, to the point that I believe minute for minute, a man or a woman is better served engaging in resistance exercise than aerobic exercise. I stand by that very, very strongly because of the evidence that just suggests how critically relevant muscle mass is in longevity and lifespan and overall quality of life. What good is it living an extra 20 years if you're sitting on a couch or in a bed? We want those 20 years. We want to square off the curve of mortality rather than having this slow decline. We want to stay functional, and then drop dead. And muscle mass is largely the predictor of that phenomenon. And so we need to make sure we train like it. And so I don't mean to sound kind of derogatory by saying it this way, but I will sometimes joke, maybe to my sisters, women need to train like men. And I only say it that way because women tend to have an aversion to actually exercising in a resistance fashion to fatigue. There will be this, I'm lifting these 10-pound dumbbells and I do it 10 times and I'm done. And she didn't even come close to fatiguing the muscle. And moreover, I was making little biceps curls, and I'm actually very opposed to biceps curls. I don't like isolated exercise. I like complex movements. But nevertheless, whatever she's going to do it to fatigue. And so if the woman wants to lift a lighter weight, well, then do it to fatigue. Stu Phillips, professor in Ontario, it's funny, we're both, you and I, Stephanie, I believe, are from Canada. I'm from Alberta.
Yes.
I keep invoking these Canadian scientists. He published a paper finding that the level of hypertrophy in an older adult human was the same whether they did a higher weight with fewer repetitions or a lower weight with more repetitions. As long as they went to failure, they had the same degree of muscle growth. Even when they were older, humans are capable of growing their muscles even well into their 60s and beyond, depending on where they had been before that. So a woman needs to appreciate the value of resistance training. I'm deliberately saying resistance training and not lifting weights because they're not, I don't believe they're the same. I resistance train every day and yet I don't lift weights. I lift my own body in various ways. So I just do body weight based exercises, but I do them at a very high tension and I go to fatigue. That's how we need to exercise in order to promote muscle growth. So that is the stimulus for the muscle growth. With menopause, I actually like the way you said it. There's an opportunity for her now that her body is her own. Where she doesn't have to worry about growing another baby in it, and she doesn't have to worry about nursing that baby. And so, as you noted, maybe now is an opportunity for her to get a little more aggressive. If she hadn't been for whatever reason, couple that with the fact that she also does not have this fat kind of hyperplastic stimulating effect of the estrogens. The opportunity here would be that with the loss of the estrogens, there's less of a stimulus to make fat cells. And indeed, her fat cell number will start to go down in around her 60s. That does happen in men and women. And I think if an adult can couple that with aggressive lifestyle intervention, then the opportunity is to, in fact, get leaner than they were before. Then now we couple it with not only with the stimulus for growth, but the fuel for the growth. And the fuel for the growth it's primarily just calories. Make sure that you're eating enough, but fat and protein are a uniquely favorable anabolic mix. Not only is the protein providing the building block, like the leucine you mentioned, these amino acids that we need for muscle growth, but the fat helps further with the energy, and it helps us digest and absorb protein better. When people have all heard of bile. Bile is something that's released into the intestines when we eat fat to help us digest fat better. Most people don't appreciate the fact that bile also facilitates protein digestion. And in the absence of bile, like if we're eating protein alone, we will not digest that protein as well. And we'll leave a lot of it in our intestines unabsorbed. We don't get to it. And so another reason why we should have the fat and the protein come together. And the timing of it isn't overly important. Another work of Dr. Stu Phillips is that a lot of people say, oh, you got to get your protein 1 hour after your workout. In reality, it's kind of like a big barn door. It's not a window. As long as you're just getting adequate protein in kind of a daily amount, then you're fine, or even multi-day amount, you're fine. You're getting enough. But I feel so strongly about this fact that protein and fat should come together that it was actually something I wanted to help people with. And so I worked with one of my brothers actually, and we created, I just feel compelled to mention it, a meal replacement shake. And it is a meal replacement, and it is built on fats and proteins. The best fats from nature, like ghee and coconut oil and olive oil, and the best proteins and collagen and some probiotics. So I basically wanted to take what I learned in the lab and everything we've been talking about. And so often I talk about these ideas and someone says, okay, great, Ben, thanks. Now what? And this is simply a way for people to make it easy. If they don't have time to plan and prepare a perfectly balanced meal, then they can just sort of get some of this shake on the go. And I won't say any more about it other than anyone who wants to learn more, go to a website called Get Health, and health is spelled HLTH, so GETHLTH.com. Not only can you see all my blog posts, including one I just released today about alcohol metabolism, but also just learn more about the shake, and if you're interested. I'm an enormous defender of saturated fat. It is one of the natural fats. It comes in coconut oil and any animal source fat. And saturated fat, it actually has a gut protective effect. A lot of people nowadays are very rationally interested in leaky gut. And it is a real phenomenon where the kind of integrity of the gut becomes a little compromised, and you get little gaps between the gut cells that allow stuff to kind of seep through from the intestines into the body. It is known that saturated fats will seal those little gaps between the cells, whereas polyunsaturated fats actually aggravate it and open those little gaps. And those are the fats that primarily come from the industrial seed oils like soybean oil or canola oil, etc. A lot of people are becoming very aware of seed oils, and I won't say any more than that in this context. But even at the level of the gut, these high levels of polyunsaturated fats will promote the gaps between gut cells, increasing the likelihood of developing leaky gut, whereas saturated fats have the opposite effect, sealing those gaps up, allowing the gut to have a very high level of integrity and make sure the only things that get in are the things we want.
A lot of people in the morning, right? Typical breakfast is usually like kind of some sort of dessert. It's like a muffin, right? It's cereal. So I actually think that this is a nice way, if you're short on time or skill, right? If you're like, I don't know how to make eggs, or I don't know how to do poached eggs or whatever, this might be a really nice replacement, let's say, for the lack of skill or the lack of access or time, and you can get the proteins and fats that you're wanting.
Oh yeah, that's you stated it perfectly. Yeah, my view and my hope when we developed it was that this would be an option for people when they can't and when they don't have time to make some good steak and eggs or cook a roast in these really deeply nutritious foods, which are the best foods. Then here's an option where they know they don't have time for lunch, so they put 2 scoops in their shaker bottle, they take it to work, and they'll put in the water and prepare it at work when they need it. That's one of the main ways I actually eat it, for example. It's just so convenient. So it's a nice, convenient way to ensure you're getting the right nutrition and not kind of knocking your body off the metabolic track that you're on. As we've mentioned fasting, and I'm such an advocate of fasting, it is such a wonderful way to just reset and almost immediately begin to improve your insulin sensitivity. As people are becoming so enthusiastic about fasting, which again, I endorse, I think it's very important for people to know that how you end a fast is more important than how long you fast. I just see this happening more and more, where people start to use fasting as almost a kind of glamorous binge purge cycle, where they fast for 36 or 48 hours, and then they get so hungry, they don't really have a plan, and they just binge on junk food. They eat themselves full to the point of bursting, and they're sick. They are ashamed. They literally feel sick. They don't sleep well that night because they're digesting and their body temperature is so high. Their heart is pounding because of all that digestion. They wake up the next day, and all that shame basically tells them, you can do better today. Do it again and cleanse yourself, and then they get into the same habit. And so my strong recommendation is how you end a fast matters more than how long you fast. So have a firm plan. Have the plan in place and recruit help to stick to it, because fasting is incredibly powerful, but it needs to be coupled with well-formulated diet and particularly well-formulated meals on the back end of the fast. And maybe that last comment would be breakfast. As you noted, it's particularly tragic in my mind that a person overnight has cleared all their food out. Their glucose and their insulin levels have come down to a nice low level. As insulin comes down, fat burning starts to ramp up. And then what do? The moment insulin has come down, we immediately spike it with these high starchy, high sugary foods. And the conventional common eating pattern nowadays is that they spike the insulin for breakfast and they do it again for their mid-morning snack and then their lunch and their afternoon snack. And a person is essentially spending every waking moment in a state of elevated insulin, ensuring that they're not burning fat and further promoting insulin resistance. So be very, very smart with breakfast, or to say it again, just be smart with how you end a fast, even if it's just your nighttime fast.